GPS is a part of our daily lives, so let's talk a little bit about how it works and how we can use it in our own designs. The GPS satellite network consists of about 30 satellites that are constantly orbiting the Earth, about halfway between low Earth orbit and geosynchronous orbit. So they don't synchronize exactly with the surface of the Earth. But what they do is orbit in such a way that pretty much any location on the surface of the planet can see between 6 and 8 of these GPS satellites. And by receiving radio signals from them, they can, a GPS receiver on the surface of the Earth can figure out its specific location. The way that this works is that each of the GPS satellites in orbit around the Earth have a very precise atomic clock on board, and this atomic clock keeps a very specific time. It's a coordinated universal time that is very extremely precise, about as precise as we can possibly get with modern science. Now, besides having this very precise time, ground stations on the surface of the Earth also keep track of each of the GPS satellites and tell the satellites themselves their specific location. Now, at any one moment, each GPS satellite knows not only its specific time, but its place in Earth orbit. So it knows exactly where it is and it knows exactly what time it is. Using this information and a big array of these satellites, a receiver on the surface of the Earth can receive the radio signals from each of these GPS satellites. And what the satellites are transmitting is their current time and their current location. So every time the satellites update, which is about once per millisecond, they broadcast out to anybody that's listening on the surface of the Earth their specific location in Earth orbit and their specific time, whatever the current time of the transmission was. The receivers on the surface of the Earth, which might be your smartphone or it might be a GPS navigation device or something like that, receive those signals and figure out, based on their current time, the signal, the time of the receiver, how long it took for the radio signal to go from the GPS source to the specific receiver on the surface of the Earth. They get a time of flight between the satellite and the receiver itself. The receivers use their internal clock to do this. So they have actually 4 variables that they need to solve for: their current time, the 3 dimensions in space, so X, Y, and Z, the altitude on the surface of the Earth. To do this, you need a fix of at least 4 satellites. You have 4 variables, and that creates a system of equations, and you can solve for the unknowns in that system of equations, those 4 variables, if you have 4 measurement points. Once we have those 4 measurement points, we can locate ourselves with a GPS receiver literally anywhere on the surface of the Earth, or actually anywhere in Earth's atmosphere. The GPS characteristics are really fantastic. The first biggest benefit is that we can locate ourselves anywhere on the surface of the Earth that we can receive the GPS radio signals. We get about 3 to 5 meters of accuracy, so about in imperial, it's about 10 to 15 feet of accuracy, which is pretty good for most applications. The maximum position update is 100 hertz. The GPS signals are sent out at about 100 hertz, but once per 10 milliseconds. We don't often use that update rate because there's a lot of noise in an individual measurement, so the receivers typically take between 10 and 100, averaging they average measurements over 10 or 100 samples in order to get a more precise measurement and try to get that error down. So we typically see GPS receivers that have about a 1 hertz or once per second or 10 times per second update cycle. The major limitation with GPS is that the signal is massively weakened indoors. Concrete structures and plumbing and metal reinforcement of buildings and things like that massively attenuates the radio signal that we get from the GPS signals. So devices that use GPS indoors get a really unreliable signal, or they're not able to get a fix on the satellites.